So now we're going to talk a little bit about scheduling policy. So everything that we looked at previously, limited direct execution, is called the mechanism. So if you have multiple processes which want to run on the same processor, what are the mechanics of getting them to run safely on the same processor? As we saw before, we want it to be fast and we want it to be safe, and limited direct execution achieves that. But a different question is, if you have multiple processes that want to run on the same processor, which one should you run first? So that part is called policy, right? So this is one of the big themes in computer science research, and I imagine in many other kinds of research. So limited direct execution is mechanism, right? So basically how you time share between different processes, and policy is which one do you want to run first, like in which order do you want to run three different processes which are all eligible to be run, right? So this separation between policy and mechanism is a very good design point. So you want to design a system such that the same mechanism you can support a wide range of policies. If, for example, your mechanism is such that the only policy you can execute is like a single policy, and if you wanted to try a different policy, you have to redo the whole system, that's a bad design. So you want to separate these two things out. So you want to design a system such that a single mechanism, or the mechanism that you develop, is general enough to support different policies. Because inevitably, as time goes by, the policy that you want to implement will change, but hopefully the mechanism can stay the same, right? So to make that more concrete, the problem with scheduling policy that we're looking at is this. So we have, let's say, process P1, process P1, P2, and P3 which want to execute, right? You have one processor, and then you yourself, or the OS, who now has to decide, like should P1 run or P2 run or P3 run, right? So this is this is called scheduling policy. Like, how do you decide between different processes that need to run, right? And there's actually like a fair bit of detail, and a lot of people have done research over the years to figure out how to do this in sort of like an optimal way. And to do this, you actually need to have a certain set of assumptions. So let's sort of like talk about that. So we're going to start off with a set of assumptions, and these are not going to be super realistic, but we will relax them as we sort of like go along, right? So one assumption that we're going to make initially, at least, is that your running time, so your process needs to run, let's say, for 5 seconds, we call that the running time, let's just call it R, is the same for all processes. So that's one assumption that we're making, right? And it's not a very realistic assumption. Different tasks need to execute for different amounts of time, but let's sort of like go with this, right? So we're assuming that the running time is the same for all the processes, and we're also assuming that all processes, what am I doing? All processes arrive at the same time. So basically, if you are the operating system and you need to sort of decide something, you can have this global view of all the different processes that can run at this point of time, and they can decide, oh, like, let P1 run, right? This is also not realistic, because like what usually happens is that you're running something, and then like eventually after some amount of time another process comes along. So this really doesn't like capture that. But again, like let's continue with this. So another thing we're going to be assuming is that everything just uses the CPU, right? As a reminder, that's the central processing unit. What this means is that they don't use any devices. So they don't try to write to files, they don't try to like display something on the screen, stuff like that. All they do is like they crunch numbers, let's say. And your job is to decide between these different processes which all crunch numbers. Again, somewhat unrealistic assumption, right? And another assumption that we're going to make is we're going to say we know the runtime ahead of time. So basically, when a process says, give me some time on the processor, that processor also says, I would like to run for like 10 seconds, right? And processes don't usually normally know that. They don't really normally know how much time they want to run. They run until they end, basically. So this is again an unrealistic assumption. So why are we making all these unrealistic assumptions? To see like if we had all this knowledge, can we make an optimal decision? And as we relax some things, we can sort of like get to a different optimal decision. But we make simplifying assumptions initially, and then we sort of relax them. And this is another sort of like general trend you'll see in CS research, is that when you have a hard problem to solve, you simplify the problem. You try to get like a very simple model of the problem, try to see how well you can do there, then you relax some of your assumptions, and then you see, oh, like in a realistic scenario, like how far away are we from our optimal solution, right? Okay, so let's sort of like, given the assumptions that we have, let's sort of like look at like different policies that we could execute. And how are we going to figure out if like the processes are good or not, right? So we have different metrics for that. So one of these metrics is called turnaround time. So you have three processes, P1, P2, and P3. And then let's say we execute P1 first, and then 5 seconds later P2, and then 10 seconds later P3, right? They all arrived at time 0, right? So the turnaround time is basically 10, right? The process P3 arrived at 0. And then it waited until 10. So the difference between these two things is basically your turnaround time. Turnaround time for process P2 is 5, and P1 is 0. Now, the reason this is an important metric is this captures how responsive your system is, right? So if process P4 came along and then it was scheduled at like time 1000, that's a system where like, P4 had to wait a really long time to get any service. So turnaround time is basically how quickly are you sort of like getting through different tasks. And typically what we do is we look at the turnaround time for each process, and depending on the system we're building, we either look at the average turnaround time, or we look at, let's say, the max turnaround time or the 95th percentile turnaround time, and so on, right? So that's one metric that we're looking at, which is turnaround time. Another metric we look at is basically throughput. So you have a bunch of processes. How quickly can you finish all of them? So in this particular case, let's say the amount of running time required was like 5 for P1, 5 for P2, and 5 for P3. So at time 15 seconds, right, we have finished all three processes. So our throughput is basically 5 seconds per process, right? So that's really like the how quickly can we get through different processes. So throughput is another metric that we look at. Yet another metric that people are interested in is called fairness, right? So imagine we had this situation where, instead of like giving every process its sort of like fair share on the processor, we kept giving P3 all the time, right? So this would be great for the turnaround time of P3 because it would be 0, right? It would be running all the time on the processor. But the fairness part of it, where like P1 and P2 like are really starved, they're waiting for the processor, they're never getting it, fairness would be fairly low. So that's another thing that we're looking at. And a slight variant on turnaround time is called responsiveness. So this is basically from the time until process arrived, when is the first time it was scheduled, right? So we're not looking at it like, like over the lifetime of the process, like, how long it waited for the entire process. But basically it arrived at some time T1. What's the gap between when it arrived and when it was first scheduled, right? So the reason we are looking at this stuff is because for interactive processes, right? So let's say you're typing something on a terminal, right? You don't want to wait too long to get a response back. But it is okay, for example, if it says like I'm working on it, like, and you will get the response back in like 10 seconds. But to even get that message to you, it needs some processor time. So in a system with like like fairly quick response times, the system basically can tell the user I'm working on it, give me some time. so that the user has some context of like oh, system is working on it, like something is happening, and the user is happy. Systems where like you submit a task and then for a long period of time you have no idea of like what is going on is a poorly designed system. And so response time is really important for the user experience part of it, and that's really like why we're looking at it. So now that we've looked at the assumptions and the metrics that we use to evaluate different scheduling policies, next we'll actually take a look at different scheduling policies.